Hey everyone, we're looking at the delayed choice experiment, sometimes it's called, or the quantum eraser demo. Same thing. So I'm going to just run you through or show you what I've demonstrated in the past in in-person classes, so you can appreciate the weirdness of it. So the Copenhagen interpretation we talked about, right, states that the measurement change in a quantum system can play a key role in observations and so on, and what's seen. And so, the measurement disturbance, right? The following demo will show that looking to see which slit particles of light went through will change the observation or the results observed. I can actually demonstrate this in a class. It's kind of crazy. And then the second part of it's even weirder, the delayed choice experiment. So we will also see that the particles exhibit a delayed choice. So a choice as to whether or not they're going to behave as a wave in the past. It's weird. Okay. So yeah. So this is just notes to self about setting it up. I can skip that, I guess, right? So what we have, laser pointer towards two slits, right? And you want to have the wall pretty far away, but you're going to see an interference pattern on the wall. And so, of course, there's answers for this below here, right? So give an explanation based on the wave model of like, well, we know that if it's a wave, then different path differences, between the light coming from slit 1 and slit 2, they can arrive in and out of phase and so on. So we've done that, been there, done that. Particle model of light. So how can you explain this, interference pattern based on the particle model of light? And your basically answer is we can't, right? So yeah, that's pretty much it. And then how can we describe it based on the quantum model? Of course, then light. The graph's all messed up here. One sec. So light interference is a quantum phenomenon, right? Where you have particle light and wave light behaviors. So each photon can go through one side or the other, or does it go through both, or whatever? So we're going to explore that using polarizing filters, right? So how it works. This is just a picture of it going through through it there. Anyways, so this is what you see on the wall. See the classic double slit interference pattern, and you've got interference within the single slit pattern as well, right? The pattern, if this was just a big blotch with no destructive interference, and then a blotch here and then a blotch there, that would be your single slit interference pattern, right? You need to know that, of course, to have this make sense. But so you cut up tiny pieces of polarizing filter and you put them at right angles to one another, and then you put it over the two slits so that the right slit's going through the horizontally polarized and the left slit lines up with the vertically polarized. So it's pretty tricky thing to do because the slits are super close together, but I managed to make it work. I have video evidence or photographic evidence as well. Anyways, and so what would you expect to see? Well, I feel like you'd probably still expect to see the wave interference pattern still, but what actually happens is the interference pattern disappears. So the quantum mechanical explanation for this is what would you expect to see based on like the Copenhagen interpretation, I suppose, right? But yeah, the quantum mechanical explanation is that if the photons can't have gone through each because you can tell which one they went through, then they can't interfere. And so the measurement changes the result. The fact that we still have light going through each, but you can tell whether they went through the left or the right slit. And so they don't interfere like that anymore. Now, there is still a single slit interference pattern that what happens is you'll see the destructive interference in this goes away. Some people would sort of, talk a little fast and loose about this and basically describe it as acting like a particle instead of as a wave, but really there's still wave-like behavior, it's just slightly different. So there's the two polarizing filters taped over the two different slits in my classroom. And here's the result on the screen, right? When you do that, you end up with just the single slit interference pattern showing up. Yeah, some people would say there's no interference, but there is, of course. You can see the rest of the pattern. Yeah, so looking to see which slit the photons go through, destroys the two slit interference pattern. And then here's the kicker. But wait, there's more, right? As if that wasn't weird enough. some extra information that you need to know to get the next part here is that, of course, a polarizing filter, would let just horizontal and just vertical, right? So if you had them at 90 degrees, nothing's going to get through. But turns out there's quantum mechanical, there's equations that you can describe this, and you'll see later on if you go on in physics. But you can figure out the percentage of light that will get through if they're at various angles, and at 50%, at 45 degrees, 50% gets through, as it turns out, right? So what you can do is later on, so when you first look at this, there's no 40 degree filter in there, okay? So you're looking at the single slit interference pattern, essentially, right? Or what some people might refer to as incorrectly as no interference, right? Because they're just looking at that center area. Anyways, so yeah, like that. This is with the two polarizing filters in there. You can see, right? If I take this thing, this is a little like a little way I just made on the notebook slide here to be able to show you. But you slide this thing in front, and all of a sudden you get that double slit interference pattern. So the interference pattern, double slit interference pattern returns. Because now there's a 50-50 chance of the light having gone through either slit, right? So this is if, excuse me, this is if you're, well, okay, the weird part about this is that you could put this filter way afterwards or before and it would restore it. So the delayed choice idea is the light goes through here, right? And then later on, so because we're looking at it, it doesn't interfere. But then later on, you release that information, you can no longer tell which one they went through, and so the interference comes back, right? So several meters away, the light then decides like, oh, actually, yeah, we will interfere. It's kind of weird, right? So restores that 50-50 chance. The double slit interference comes back. Kind of bizarre, right? So please understand the significance of this, right? The interpretation of the two slits being blocked by light through each, yeah, is polarized by 90 degrees from another, so you're blocking light. It's thought it was forcing photons to give up their wave properties, and by you're observing which slit they go through, right? So the interference pattern disappears. But now, afterwards, way later on, this act of observing light has made the wave properties disappear. The 45-degree polarizer brings that property back. So this shows to be people, whatever. This shows that the it's not really wave or particle. It's kind of wave and particle, of course, right? As we've already been talking about. And de Broglie has the wavelengths of particles, itemized out and measured and confirmed. But somehow the photons are able to go back in time and change their mind as to whether or not they went through both slits or not. After the wave properties have been given up, they can go back and not give up those wave properties, right? So that the choice about interfering or not apparently can be delayed or decided later, or however you want to think of it. It's kind of bizarre, right? So does the photon go through one side or the other or both? As seen in these demonstrations, you can only get an interference pattern if you can't tell which photon path the photon followed. In those situations, each photon has a probability of getting through each one, and Schrodinger wave equations, they for two paths interfere, resulting in that interference pattern, the probability of landing interference pattern on the wall. The math is very precise and gives accurate predictions of the results, but it doesn't explain physical reality of things, right? It's a mystery to us still. Absolutely, it's a mystery to us still. So video of this guy here. Let's just go to my, easier to find it. So this is just a quick little video where at first you've got the single slit interference pattern, basically no interference in this central region, right? And then you're going to see it bring in a polarizing filter. And when I turn it angle to different angles, you're going to see glimpses here. It's a little bit, there we go. Little glimpses. You can see an interference pattern show up. And it's pretty touchy, but also pretty convincing. Kind of weird, right? So yeah, single slit pattern at first is known. Yeah, when it's known which slit the light went through based on the polarization. Then of course the 45 degree brings back that 50-50 chance. And as we said, this is all redundant really, right? So yeah, so you'd think real tangible particles would have had to have destructively interfered or not. But that's just, and that would be fixed, but it's not apparently. It's weird and it's quantum. We shouldn't be too surprised that it's weird, basically. So So it's just a quick video today to show you that weird result, and there's some extra videos here for you to watch to do with it if you want more. The note back or think back to the fact that we thought about polarization as basically being described based on wave properties. But the description fails if you reduce light intensity down to single photons, right? So it's a little bit weird. So we got to pay attention to the fact that it's quantized, of course, right? Light itself. So really, polarization, as it turns out, is really a quantum mechanical property. It's not just the direction the light is waving or whatever as a wave. So photons are polarized as well, right? Yeah. And then, of course, all those different polarizations exist in all possible states and so on. So interpretations of things, I guess, but yeah, that is the quantum eraser or delayed choice experiment. Please, yeah, go ahead and I encourage you, please watch those other videos as well. Could be some information in there that on a test or something for you. So anyways, please watch them. And that's all for now. Talk to you later. Thanks for watching.